Hello, welcome to the discussion on Midsem model question that I have shared yesterday. Let us look at the first question. Before that, let me tell you what we plan to do in this exam. We will give you the question paper, and this question will also have those set of branch instructions, different conditional branch instructions. That table will also be attached, and then there will be few blank sheets attached with the question paper where you only need to provide the answers, and then return along with the question paper you will be returning your answer sheet. So there won't be any separate answer booklet given for this exam, and the total marks is going to be 30, and the weightage is also going to be 30. Duration is 1 hour 30 minutes, and it's going to be on 19th May in the morning, mostly 9:15. Okay, we'll start at 9:15 and get over by 10:45 so that you will have a classes starting from 11:20. Okay, let us now get into the solution part of it. Though I have given these questions, the discussion that I am going to do now is likely to be on more stuff around this question. The reason being that you are likely to get questions around the discussion that I am having, because the same questions won't come in the final exam. So please listen to this lecture and understand all the points that I talk about every question. Okay, because it's not only the particular answer here, I'll be talking something around that so that you get more information about those topics that we are seeing here. So let us look at the first question, which is about the RISC machine. Now all of you know that RISC machine is a reduced instruction set computing. That means there are many instructions which are operating only within the registers that are there in the CPU. Okay, that means the operands are operands, which are the values that these instructions operate on. They come from other registers. R0 to R15 are the registers, so they come from other registers, as well as immediate constants. So immediate constants are part of the instruction itself, which is inside the CPU already. And suppose if I am saying move R0 comma hash 5, this means this 5 is already there along with the instruction which has been read into the CPU. So moving this value into R0 is nothing to do with the memory access. Remember, this value is not in the data memory. It is part of the code which has come inside the CPU. So do not get confused that move R0 comma hash 5 is actually the 5 is coming from the data memory. No, it's the part of the instruction itself which is already read by the PC program counter, and this will not take too much of time in getting this value into the register. Now there it's not memory operation also. Now what are the instructions which support memory operations? LDR, all the family of all the instructions, LDR-SB, LDR-B, LDR-H, LDR-SH, all of them, all the instructions load some value from the memory into the CPU. And where does it come? It will come into the registers of the CPU. Now what about STR? This instruction stores some values from the registers into the memory. So it is also having different varieties: STRB, STRH and STR. And LDR, STR are 4-byte wide data which is getting read or stored, whereas H is half word, which is 2 bytes, and then B is single byte. So our question is, what type of instruction that operate on the data in the memory? So it is not talking about the code area, it talks about the data area. That means we are trying to access the data portion of the memory into the CPU, or we are writing into the data memory of the program. So load instruction reads from the memory, and store instruction stores some values from the registers to memory. So both are operating on the data memory. So the correct answer is C here. Okay, I hope this is clear to you. Now what about RP2040, whether they are 8-bit wide, 16-bit wide, or 64-bit wide? See, all the registers within this RP2040 have many times told they are 32-bit wide. Okay, that means B0 to B31. So none of the given options are correct. So D is the right option. Now this I am going to spend little more time than the question says, so there are basically stack. Let me draw different stack memories. Now let me give you some overview which I have already explained, may not be recorded, so it is better I have a recording of what I am saying now so that you have a clear idea. So stack, you know that stack memory is pointed to by stack pointer, which is R13 register in the CPU. Now, where does this stack reside in the memory? It's in the read writable memory, because if you are declaring a local variable which is going to be in the stack, and you should be able to write into the local variable and read from the local variable. So it should be read writable memory, and it should be in a data memory. Okay, it's not cannot be part of code memory. Now the processor CPU is operating on the stack. So there are many ways the stack can grow. So let me say that this is a higher address, means if I say 1004 is here, 1000 may be low, right? Below, immediately below that. So higher addresses are in the top and lower registers are here. Now a stack, what happens is you keep putting some data into it, it grows, and then when you take data from it, it is shrinking. So always the data which is in the top of the stack will be extracted out, or you will be putting this new data on top of the already existing data in the stack. So now let us look at different ways of operating the stack. Imagine a stack is growing towards the lower address. Okay, let us assume that these two stacks are going towards lower address, and these two stacks are going towards the higher address. That means when I keep pushing data, the stack is going to go down. That means the stack pointer address, whatever is there, is going to be decremented by how much of value I am copying into the stack. Now always remember, in the RP2040 we are going to have a 4-byte wide stack. That means any stack operation is in terms of 4 bytes. You cannot push only 1 byte into the stack. Even though the actual data value may be 1 byte, but you will always push 4 bytes into the stack. Now, I said that stack can grow downwards. These two are some examples, and stack can grow upwards, and these two are which are growing towards the higher address. Even within the stack growing lower address, there can be two ways it can be done. Now suppose already a stack pointer is pointing here in a given address, you can assume that a valid data is there already in the stack. Whenever I want to push something into the stack, I will decrement it and then push into the stack. Okay, new data, first new data of push operation will come here. Now next push if I do, I will decrement it again, and then another new data I put it here. This is called, let me maybe take more space here. So this stack which is going downwards is descending stack, not ascending stack, because every push is going to go take the stack towards the lower address. Now there are two ways of descending. These two are descending stack, but this is full descending. That means the stack pointer which is pointing at is full, and then when I am pushing it, it is going to go towards the lower address. This is called one type of stack. Now what is another type of stack? Suppose stack pointer is here. When I push it, it will push the new data here and then decrement it. So that means pushing the data into the stack happens first and then decrement happens. Whereas here decrement happens first and then pushing happens. So this is also descending stack, because it's going towards the lower address. Stack is growing towards the lower address, but it's empty descending. That means where it is pointing at is a empty location. So I will put the data here and then decrement it. So once you have understood this, then you know what I mean by full ascending stack and full descending stack. Empty ascending stack. This I will call it as, let me write it here, empty ascending. Now what does it mean? I am talking about going towards higher address. Okay, stack is. So if I am talking about full ascending, it is pointing at the full location, and if I have to push the data, I will be incrementing the stack pointer by 4 plus 4. This is minus 4, and then push a new data. New data 1 will be here. Another new data, if I push, it will be here. And this exact reverse will happen when I am popping it out. Whereas empty ascending, it is pointing at empty location. So new data 1 will be here, and then I increment it and then put it here. So that means I always make it point to an empty location. So always remember that when I do a push operation, either plus 4 will happen or minus 4 will happen. It has to happen. But whether it happens before the data is pushed or after the data is pushed is what is difference. Similarly, when pop is happening, it has to take the data out and then reverse the operation it did during the push. So ascending and descending and full and empty are the 4 different types. I hope this is clear to you. Question may come from any of those 4 types of stack. Okay, that's why I'm explaining everything and have a clarity on this, and there is a slide on this exactly, and please follow that. Now let us look at the question here. If a processor supports empty descending, now based on this you should be able to just draw a stack of your own thing, and then it says empty. Let me see what this question says. Empty descending. So let me write it here so that you understand how empty descending works. That means the stack pointer is looking, pointing at an empty location. So this is empty. Descending means this is a higher address. Suppose you assume that this is a higher address, this is lower address. The stack is going to go or grow. It is going to grow towards a lower address because it's descending. It is looking at pointing at the empty location. That means if I do a push operation, the new data, whatever push I am doing, is going to sit here, and then I am going to decrement it. Okay, that's all is. And how I am going to decrement it? I am going to decrement by 4 because the stack width is always 4 bytes. Now, which are the options as correct? If a processor supports empty descending mode of stack implementation, then a new data will be pushed into the stack. See, I may ask you even popping a value from the stack. Here it is pushing, so you have to imagine pushing, and then what operation will be done? Because it is going to be pointing at the empty location, the data should be copied first. So copying the data first happens. Okay, you have to now localize to these two options. Copying data happens first because it's an empty location. You have to copy the data first, and then are you going to increment the address or decrement the address? Descending means you are going towards the lower address, so you should be decrementing it. So this, out of these two, you know which one to select. Copy the stack data first and then start into the stack before decrementing it. So you are going to decrement it afterwards. Okay, so this is the correct answer. D option is the correct option for this question. Okay, I hope if I ask you push or pop or any of the different 4 types of stack, you should be able to answer the question without any confusion at all. Okay, that's the reason I am explaining you everything. I'm not talking about only that particular question, only to keep you aware that a question can come from any type of stack. Okay, fine. Now I hope this is clear. Address loaded into the stack pointer, which is R13, should always be, as I said, stack is always a 4 byte value which is going to be pushed. So you should always have the address which is 4 byte aligned. That what I mean by 4 byte aligned, let me explain in case you have missed out the explanation that I gave in the class. Stack pointer, if I am saying that it is having a 4 byte aligned address, means whatever address I have it in the stack pointer, if I divide it by 4, I should not have any remainder. That's all. Okay, that's all I'm saying. Though no remainder, it's divisible by 4. So any address, this is not, I'm writing in 0x form. Suppose if I'm writing in 0x form, you know that the next valid address of the stack pointer will be 1008. What would be the other one? One more than this, 100C, because this is 12. And this is how it is going to be incrementing. Okay, you should know. And if it is going to be decimal value, so it is going to be 2008, 2004, 8, 2012 it will be. Okay, because I'm writing it in decimal form, there is no 0x in front of it. So the addresses will be incremented like this. I can't start or I can't load the stack pointer with some value which is 1001, and then you cannot say that I will increment by 4 and it will become 1005. In both cases, when the stack is loaded with the address which is not divisible by 4, it's going to create an exception. Exception means something happens inside the processor, its own operation creates an exception and it goes to an exception handler, which is, it will freeze, okay, it will not work further and you have to reboot your system. Okay, that's what will happen when you try to manipulate the stack values illegally. That means do not have a value which is not aligned with 4 is an illegal operation on the stack. So make sure that when you are writing assembly code or when you are incrementing the value what is there in a stack pointer register, make sure that you don't increment it, okay, in terms of 1 or 2 or 4. No, it should be always 4. I'm not talking about even the stack pointer, even the LDM, STM or LDR instruction or STR instruction, they need to be 4-byte aligned because this is a 4-byte operation, right? If we are storing 4-byte, the addresses should also be 4-byte aligned. If I am saying LDRH, then this address should be 2-byte aligned, okay? And because I am going to operate 2 bytes at a time. Now what about LDRB? That address, whatever I am giving, the base address can be anything. So remember, based on what manipulation you are doing with the memory, it should be according to that the address should be loaded into the base register. Okay. Let me explain what I am saying. LDRB R0 and R1. Now which is the base register? This is the base register. I am loading a value pointed to by R1 into R0. Now this is a byte address, right? It's loading a byte. Now I can have a value which is 1, 2002, 2003 in decimal is allowed because it's a byte operation. Whereas if I am doing a LDR operation on R0 and R1, now I am manipulating a 4-byte values, then this address should be 4-byte aligned. Okay, that's what I am saying. Now LDRH, suppose I am having, then R2, R3, then the base address should be 2-byte aligned. So it means 2000, 2002, 2004, 2006 it should be, okay, it should be divisible by 2. Keep this in have a clarity on this, okay. That could be questions based on this, okay. So that's why I'm giving spending little more time on this, because having learned all this, you should be able to, once you listen to this lecture, you should be able to answer any question that comes in the Midsem, okay. Now, what is application binary interface? All of you are aware about APIs. Okay, application programmers interface or programming interface, application programming interface. ABI is application binary interface. The word binary means it is something to do with the binary files. That means you and me cannot appreciate or understand what is there inside a binary file, right? So, what are the binary files? You know, OBJ file is a binary file. .ino file is a binary file. .lib is a library file. Okay. Which is a library, okay, which is a binary file. Now these binary files are actually generated by the tools, right? Compiler generates OBJ file, right? And it can also generate a library file if you are interested in generating a library. Now who will be using it? The tool like linker, which is also a tool, wants to merge one OBJ file with one link file, library file. He should know how to understand the code which is being called from each other, right? I am calling printf from my program, then I am calling a library function. If I am calling your assembly code from the C code, okay, I am calling another file which is written in .s and which would have been when you are assembling it, it would have generated some OBJ, and the .c would have got generated by another OBJ file which is generated by the compiler. So C file what you have, or a INO file that you have, is a C++ code which is generated by the C compiler or C++ compiler. Whereas .s file is an assembly file which is generated by an assembler. Please remember all these things, because any kind of questions could come checking you on whether you are aware of these things. So that means the two different tools are generating the OBJ files, and then they need to be able to work with each other, because when I'm calling a assembly function from C, I'm passing a parameter, they need to have a better clarity. So there is an understanding that between two binary files, how different things can work together is what the application binary interface talks about, and it's a standard, okay. So what is the right answer for this? Having explained this, I'm sure you will be able to pick the right answer. It's not interfacing executable files, because two executable files, see, though executable file is also binary, please understand, interfacing two executable file is not a thing what we are talking about. We, in fact, two executable files are, suppose I have a PPT which is also an exe file, and then maybe I have a MS Word, which is also an executable. So these two, I'm not trying to talk to each other, making them talk to each other. Okay, exe files are different. They are running as a separate processes in the system. Okay, they may have some interfaces with the dynamic link library and all that, but we are not going into those details of that. So this is not the right option. And then interfacing applications is another application. That's what I'm talking about. Two executive file interfacing and two application interfacing is same, but we are not talking about uh, browser talking to another browser or something like that. Okay, we are talking about two binary files and the development tools talking to each other. So ABI is within an application. ABI definition is used within an application. It's not across the application or across the executable file. Okay, I hope you are clear about it. So it's a B is the right option. Okay, it will be a little confusing to you, but remember, ABI is for generating one application which uses many binary files within them, like obj library, and different tools will be using it, maybe library generator, or no or uh, a linker which is combining multiple files, or it could be a compiler. So these are the tools and the binary files which are within an application. They talk to each other, where you define a ABI for it. Okay, so B is the right option. Now let us look at something. What is AAPCS? It's a ARM architecture, okay, standard, parameter passing standard. Okay, so this standard, the registers which are not expected to be preserved on function calls. So I think I have told you many times, and you have also written many assembly program. You know that R0 to R3, four registers are there. They carry some parameters. Okay, if you are passing four parameters, suppose if I am passing only one parameter, then R0 will have that value. This will be anyway available for you to use, but they are not getting any value from the calling function. This is a C calling function. This is a ESM. So when the assembly function is being called from the C using branch with the link, and then your ASM file, okay, ASM label, my ASM, okay, then my there is no semicolon here or a colon here. This is the instruction actually, branch with link register BL, which I have not told you earlier, which doesn't matter. This is a function call similar to a function call that you have in C. This is a function call routine from assembly to another assembly, from C code. When I am saying from C code, it is actually assembly, right? It is generated by the compiler. So it is actually executing a BL instruction to come to your assembly routine to execute your parameters or functions. So it is carrying the parameters from the C function based on the number of parameters you pass. Maybe R0 is loaded, or R1, R2, R3 based on number of parameters coming in, and then you operate on it, and then you say BX LR. Then you are returning back to, since you are used L here, link register is used for returning back to the calling routine. So which is nothing but R14 register. Okay, so it goes back, because R14 is going to have the address of the next instruction which is generated by the compiler below this function call. It will be coming here and executing. The PC will be loaded with this address, and then it will start executing this instruction. Okay, so what is the question now? I think this is a generic introduction I gave you, so that you are aware of any questions that can come, which you will be able to answer. So which are the registers you are free to use? When I say free to use means, even if you modify it, the calling routine is not going to be impacted, because as I many times told you in the class, the C routine is also using the registers that which are there in the CPU. Physically, there are only R0 to R15 registers, which are used by both C function, C program, as well as by your assembly program. So when you are using those registers in your assembly program, you need to make sure that you are not disturbing the state of the values that the compiler has maintained in its own register, because we are actually sharing the registers along with the compiler generated code, and we are writing our own assembly code, and the control comes to you. So it is your responsibility to go back without disturbing the state of the remaining values in the register. So you are free to use R0 to R3, and in case if you are using other registers, you have to push them when you are about to change them. Okay, maybe R5 you want to use, you have to push them, and then before you leave the function, remember to pop R5. Okay, so this is very important you to remember that. Okay, so the right answer is very obvious. It's the A option. Okay, R3, R0 to R3. Now what is this? Choose the instruction which loads 1 byte value from the memory address pointed to by the contents of R1. Okay. Now let me explain the question here. So LDRB R0 R1. Now choose the instruction which loads 1 byte value from the memory, 1 byte value from the memory address pointed to by the contents in R1 into register R0. So I happen to write the correct answer because B has to be there, of course, but there are two instructions which are having B. The other one is R1 and R0. That means this whatever is there within the square bracket is the address pointed to by. Now this says that memory address pointed to by the contents of R1. It says it's not saying R0. So this is not this instruction is not the valid instruction. Okay, this is the one which is inside the square bracket. So you have to be little careful. Okay, you might make a mistake and then say the this one as a right answer, which is incorrect. Okay, so B is the correct answer here. Now let me talk about this one. Okay, when the following instructions are executed, choose the option that describes about its return value. Let us not look at the return value. Let us try to understand this code. Okay, R1 is loaded with 0x8. So as I told you, 32-bit register, always 32-bit value is loaded. Though you are giving only the lower valid value, the rest of it will be 0. Okay, so remember B0 to B31, and 8 is in binary form is this one. So it is B3. What will be there? It will all be zeros. Okay, all these values are zeros. So where is it going? This is into R1. So R1 is having this address, this value. Now what is in R2? R2 is getting a value which is 0x 1. Okay, this is 0x1. That means R2, let me write it. All zeros are there because only one value is 1 is here. Okay, that's all. Now what is the next instruction? LSR. Okay, R0, R1, comma R2. Now R2 is a value is whenever you see here logical shift right. Okay, you should remember that. Okay, logical shift right. So you should remember this operation, and logical shift right means this whatever is value here is a unsigned value because you are not going to bother about any sign bit being extended into when you are right shifting it. Okay, ASR is there, LSR is there, but LSR is only given, so it's a 0 is going to come in, and then here what is happening? R1 will be here. Okay, and R2 will be here. R1 value is this many times, whatever is there in R2, that many times is going to be right shifted, and the result is going to be put in R0. So what is in R1? 8 is there, 100. Okay, rest of it is 0 here. I don't have to worry, and I am shifting it by how many bit? 1 bit. Okay, that means 100 will be right shifted, then it will become what value? 100, and all zeros would have come in, so it would have become 4. Okay, and it is moving into R0 and BXLR. That means you are going out. So when the following instructions are executed, choose the option that describes about its return value. So what is going to be returned? What is there in R0 will be returned. So out of these 3 options or 4 options, 4 is the right option, right? Because 8 is shifted right by 1 bit, which will become 4, 100. So B is the right option here. Okay, I hope this is clear to you. Now let us look at the other code. Before we see the options, let us just try to execute it. Now move R0 4. So let me write it. You can also do the same way so that you will never be going wrong in the exam. What I am doing is how I will be solving these problems. Okay, so I want you to do the same in case you find it useful. Always remember that you are considering 32-bit value, that you should never forget it. Even if I am saying 4 or 3 or 2 or 1 or even 0, if I write 32 zeros are there, remember that. Okay, so always keep that larger picture in mind. R1 is 3, so R1 again 3 is 1 1, all zeros. Okay, you can put a dot. I don't want you to put all 32 zeros because time is limited in the exam, so I want you to be careful. R2 is loaded with 2, so R2 will be 0 1 0, right? 2. Okay, I think the binary form of any number you should be able to immediately get it, at least till 15. Okay, now what am I doing? Add R2 R0 comma R2. That means what? R0 is 4, R2 is 2, R0 and R2 are getting added, and then it is moving into R2. So this is having 4 and R2 is having 2. 4 plus 2 is 6. Now R2 is modified to 6. R0 still has value 4. And then I am immediately doing BXLR. Remember, there is no mistake here, or it could be intentional. Please don't try to say that no, I made a mistake, that I have not put a move R0 comma R2 or something like that. You have to go by what is there in the program. Whatever instructions are there, it will execute. So don't try to assume that there is a mistake here or anything. Now R0 is not modified at all because it's only operand, remember, and the result is going into R2, it's not going into R0. So only R2 is getting modified to 6. Now BXLR, when I do, immediately the receiving function is not going to bother what value is there in R2. It's going to look at only R0 because it always assumes that you are returning the value in R0. So the value returned by the below assembly function is 4. Okay, not 6 or not 2. So you need to be careful here because it is little tricky. You might make a mistake without paying attention to it, or you may think that the program is wrong and you will assume that 6 is what is going to be returned. It's not true. Though it's called a function is called add ESM, it doesn't have to return the added value. Okay, I may make a mistake. Okay, so please remember that. Very good. Now finally, 10th question. Write the type of stack supported by ARM Cortex M0 Plus. Okay, always remember it is not the RP2040 which is supporting a particular type of stack. It is a Cortex, the processor M0 Plus, which is supporting the particular type of stack, which is full descending, which you need to have remember by now. This is the full descending and you need to explain about what is full descending. It is going to be full SP is pointing here, and then descending means is going to, when it is pushing it, it is already pointing at a filled location, so it should decrement it and then push the value. New value will be put here. So you need to explain it like this with a small picture. Okay, write the type of stack supported by ARM Cortex and provide a short description. Okay, maybe I should have added that part of it. So just full descending. Actually, okay, I'm sorry. I think full descending is enough for you here because it's a one mark question. So I want you to just write full descending. No description is required because it's a part A question for that matter. Okay, I think we have exceeded the time limit, so I will stop here with the part A solution and part B in the next video. Okay, bye bye. Hope it is useful to you.